Hello everyone, for this tutorial video, I'd like to explain how to solve more intricate and less straightforward applications of the substitution rule. For example, if we are given this integral, we see that we no longer have two neat functions with one inside and one outside, but rather a more complex group of different types of functions that are not related to each other. However, we can see that 2 times t is a common argument throughout all these functions. So the differential of u is 2 times the differential of t. In conclusion, the differential of t is 1/2 the differential of u. So we plug this in and factor out the 1/2, and also substitute in u for all of the 2t's. We take the integrals of the individual functions with respect to u, and finally substitute back in 2 times t for u. If we are given an integral like this with fractions, we see in this case u equals x squared plus 1. Differential of u equals 2x times differential of x. So x times differential of x is 1/2 differential u. We see that x factors out as a common term in both functions in the integral. So we can substitute in 1/2 differential u, as well as the u for the x squared plus 1. We integrate the two functions with respect to u, and finally plug in x squared plus 1 for u. Sometimes you will actually have to do more than one substitution at the same exact time as this function shows. We first break up the integral so that all terms in the numerator are the numerator of individual integrals. Get the right-hand integral in terms of an integral we know by multiplying everything by 1/16 to get it in the term x squared plus 1 in the denominator, which we know is the derivative of the inverse tangent. We see now in the first integral u equals x squared plus 16, so differential of u equals 2x times differential of x, and x times differential of x is 1/2 differential u. For the other integral, we see x squared over 16 is x over 4 squared, so we plug in a different substitution which we call v for x over 4. We see differential of v is 1/4 differential of x, so differential of x is 4 times differential of v. We see, returning to the original integral, we have not x in the numerator, but 10 times x, so 10 times 1/2 is 5, so we get 5 times the integral of 1 over u times differential of u. And on the right-hand integral, we have 3 in the numerator, so we factor that out, and we see that something over 16 times 4 is something over 4, so we have 3/4 as our constant on the second integral. We now take these integrals and finally substitute back in the values for u and v. Lastly, we can rewrite functions that appear to be only a single function and use the substitution rule on them as well. For example, the integral of tangent is the integral of sine over cosine by definition of tangent. We see if we take u to be cosine of x, change in u to be negative sine of x times change in x, we can see that x times change in x must be negative change in u. We have sine of x times change in x in our definition of tangent, so we plug in negative change in u for this, and we get the integral of negative 1 over u with respect to u. This becomes negative ln of absolute value of u, and we plug back in cosine of x for u. Now that we have figured out more sophisticated case of the substitution rule, we can transition to definite integrals next, as well as see how we can get the literal definition of the definite integral from adding infinitesimally thinner areas under a curve. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.